Hello, future engineers, viewers, subscribers, and students. Here is a video in statics about centroids and moment of inertia of plane areas. And this is intended for slow and weak engineering students. This topic is particularly on built-up sections. So I'll explain first, one by one. So for this video, let's have wide flange first, its properties, and I want you to master, familiar with the different elements of the W flange, which is a very effective section in resisting bending moments, particularly beams and girders. So for the built-up section shown in the right part, because I'm going to discuss first properties of W flange in the left part. What should be the thickness of the rectangular plates in mm that must be welded vertically as shown so that IGX equals 6 times IGY. So here is the W flange and these are the different elements. So the section looks like that. There is a fillet here. Now, if the moment of inertia with respect to the centroidal axis, which is capital XX here, this is understood IGX, and the section is symmetric with respect to both axes. So this is IGX, IXX, IYY, which is IGY also. Now, we call this the flange. This is the bottom flange. That's the upper flange. And the width of the flange is designated by B sub F. Its thickness is T sub F. The depth of the flange is denoted by small letter d, overall depth, and the net height of the web, this is the web, the vertical part, interior, is called the web, and the thickness of the web is denoted by TW. Again, for the flange, the width is BF, and the thickness is T sub F. Now, look at very closely the details of the corner of the flange. It is fillet, meaning it's a round corner. However, also this part here and this part. However, if the moment of inertia of the wide flange is not given, it should be given with respect to the centroidal x-axis and the y-axis, then we can treat this as component rectangles. And you can compute IXX as moment of inertia of big rectangle with respect to the centroidal axis. BF and D must be given. And you can compute H, of course, it is D minus 2 times T sub F. That's why it will not be given because we can compute this. This is the thickness of the web. So you just treat this as big rectangle minus moment of inertia of smaller rectangles with their centroids still lying on axis XX because of symmetry. Same is true with axis YY. But for axis YY, we have to compute the moment of inertia with respect to the centroidal y-axis, then less the transfer formula for moment of inertia of these two rectangular components. If the properties IXX or IGX, IYY or IGY are not given, we treat this as rectangles. So that's the deal, that's the concept, that's the remedy if in case the properties IXX and IYY are not given. So these are just two examples. There are so many sizes of the wide flange complete in AISC, American Institute of Steel Construction Manual. Everything is there, but these are just representative examples in statics. So W16 by 57 and W14 by 38. And we have here areas. These are areas in square inches. It's included there, but I will label that in more detail. So the first number 16 means the nominal depth in inches, but that's not the actual depth. The actual depth will be given. It will be provided in the table. The second number is the weight per foot of the wide flange. That's the idea. So if the numbers, first number is relatively low, so it is USCS, English unit. So 16 nominal depth is 16 inches. That's the meaning of that. I'll discuss this 16 by 57. 57 is the approximate weight in pounds per foot. The actual depth of this section is 16.4 inches. And take note that 1 inch is 25.4 mm. Uh, the values here are rounded off to three significant figures only. So, but we want the accurate ones, but we can check these values by converting these values into SI, System International Units, inches to mm, pounds to kilogram per meter. So the area is 16.8. So for W14 by 38, it's 11.2 square inches. So 16.8 square inches. The width of the flange for this W16 by 57 is 7.12 inches. TF is not, this will be given in the problem when important, or when we, we should use this value or this element in order to analyze the problem. But if not needed, then it will not be given. Like in the example, in the first example later. Then thickness of web also will be given when important to the problem. If not, it will not be given. So take note of symmetry. So that's why half of BF will no longer be given. And the centroid, location of the centroid will also not be given because the section is symmetric with respect to both axes. So the centroidal moment of inertia with respect to XX, this is IGX, 758 inches to the fourth, and IYY is IGY, 43.1 inches to the fourth. So let's convert this into SI units. By the way, this 57 pound per foot can be computed if you know the density of steel, because this is steel. So if the specific gravity of steel is 7.86 and the specific weight of water is 62.4 pounds per cubic foot, then all you have to do is multiply the area to compute this to verify that it is about 57 pounds per foot. So for instance, uh, weight density of steel is specific gravity 7.86. Prepare your calculator. 7.86 times 62.4 pounds per cubic foot times cross-sectional area, which is 16.8 square inches. Because this is square inches, we must convert this to foot square by dividing everything by 12 square. So 7.86 times 62.4 times 16.8 divided by 12 square, you will get 57 point something. That's why this is 57 pounds per foot. So in SI equivalent, it is 410 by 85 because 16 times 25.4 is around 400 something. But this is rounded off to a whole number, 410. So I hope you know that. Then 57 pounds per foot, we convert this to, this is in kilogram per meter this time. 85 means kilogram per meter. So 57 pounds per foot times 1 kilogram, 2.205 pounds. So we divide that by 2.205 pounds. And 1 foot is 0.3048 meter. So we divide the value further by 3.3048, and you will get around 85 kilogram per meter. Another way is uh, 7.86 times 7.86, 7,860 kilogram per cubic meter times cross-sectional area, which is 10,800 mm square, divided by 1,000 square, you will get about 85 kilogram per meter. So that's the other way. So the actual depth is 16.4 times 25. 16.4 times 25.4, it's about 417 mm when rounded off to three significant figures. I already explained this. Then the area 16.8 square inches times 25.4 square, that's around 10,000 something, rounded off to 10,800, because the idea here is we round off values to three significant figures. BF is 7.12 inches times 25.4, so that's around 181 mm. The rest is the same. IXX is 758 times 25.4 to the fourth, so to three significant figures, 316 times 10 to the 6, and 43.1 times 25.4 to the fourth is around 17.9 times 10 to the 6. So that's the explanation. And I hope you can familiar with these elements. So don't worry, as long as you're familiar with the elements, the labeling, everything will be given. So this is the figure and this is the problem. We have W 410 by 85, so that means we use SI, this one, and the properties are already given. And we have two additional rectangular plates of the same depth as the W flange, and we find the thickness such that it satisfies this condition. IGX equals 6 times IGY. For IGX, the centroidal x-axis of the wide flange as well as these two vertical rectangular plates coincide with the centroidal x-axis of the wide flange and in general the entire figure. Therefore, IXX is just IXX of the W flange plus 2 times IX of these two plates. The IX of these two plates is base, which is thickness, height, which is the depth of the flange, which is 417 cube over 12. That's it. We don't need to transfer because the centroidal x-axis of the two plates coincide with the centroidal x-axis of the wide flange as well as the entire figure. So IGX is 316, that's IXX of the wide flange, times 10 to the 6, plus with times 2 times the moment of inertia of one rectangular plate with respect to the centroidal axis is thickness, the base is thickness, height is the depth, 417 cube over 12. Simplifying, IGX equals 316 times 10 to the 6 plus 12.085 times thickness times 10 to the 6. Likewise, IYY is IY of the wide flange, which is 17.9 times 10 to the 6. Then we add the IY of one rectangular plate, then multiply it by 2, and we transfer its centroidal moment of inertia with respect to its centroidal y-axis to the centroidal y-axis of the entire area. So the distance is half of BF plus half of the thickness as shown. So this is half of BF. BF is 181 over 2 plus thickness over 2. So that's the distance between the parallel axis. So IGY is equal to uh, 417 t cube over 12 plus area 417 times t times distance quantity 90.5 plus 0.5 t square plus IGY of the wide flange. So IGY is IGY of the wide flange, which is 17.9 times 10 to the 6, plus 417 t cube over 12. That's the centroidal moment of inertia of rectangular plate with respect to the y-axis. Then we transfer it, so plus area 417t, and the distance is quantity 90.5 plus 0.5t, then square. Then IGX is 6 times IGY. That's the condition to this problem. And you can simplify this. So 6 times 17.9, 6 times this value here. And you can evaluate this with your high-tech calculator. I will not expand this anymore. I'll just use the high-tech calculator. Then solving for the thickness, it is equal to 16.77 mm. So I hope that you understood the explanation, the equation setup, and you can do same problem by your own. So this is the first example on built-up sections. That's why I use wide flange and rectangular plate combination. So later on, as we move on, we proceed to challenge problems where we have two or more sections that are built up or combined.